Here's example one. I must have done these in the other order, but that's fine. This is the antiderivative of the square root of 1 minus x squared dx. And the picture there, just a reminder of what this function looks like. It's the top half of a circle, semicircle, because it's the positive square root of 1 minus x squared. And we did do these in Calc 1 a little bit. We did them when you were actually finding the area underneath that curve. And it would be the integral from -1 to 1, because it's a unit circle, of the top half of the unit circle. And then you would find the area was exactly, well, the whole thing would be pi r squared, so pi. So the area underneath that is half of pi over 2. But now we're trying to find the antiderivative. That was found by a trick where you could just use the usual integral for the usual formula for the area of a circle. But these are indefinite integrals, and you have to find the antiderivative. So instead of thinking of the circle, we notice that it looks like a right triangle. There's a lot of connection between trig and circles, of course. So we switch to looking at it as a right triangle. It has a 1 minus x squared, so this is similar to the last problem. That should be the adjacent side of that triangle. I drew the triangle underneath down here. And then the opposite side should be an x, and the hypotenuse should be a 1. Double check that that works with the Pythagorean theorem. And then the sine of the angle theta will be the opposite over the hypotenuse, or x. This time I don't even have to solve it. I just say x is equal to sine of theta. And I've written that up on the same line as the original integral. So dx is cosine theta, d theta. We've moved the d theta over. And there's a couple of ways of doing this again. You could do the algebra and see what's underneath that square root is 1 minus x squared. So it's 1 minus sine squared, which is equal to cosine squared, and the square root of cosine squared is cosine. And then however, it is exactly found by looking at the triangle too, which I wrote at the bottom here underneath the triangle, the bottom of the screen. Cosine of theta is just the adjacent over the hypotenuse, so cosine of theta is 1 minus x squared. So either way you do it, you also replace dx with cosine theta d theta, and so by the third line you have cosine theta times cosine theta, which gives you back cosine squared theta d theta. It looks a little bit weird, but it's, if you're looking at from line 2 to line 3, you took the square root and got rid of the square, but then you had another cosine theta multiplied onto it, so it's cosine squared again. Now that we have to use the standard trig identity. Cosine squared is 1 minus cosine 2 theta over 2. I've written that as two fractions. Cosine squared is 1 minus cosine 2 theta over 2, but I put the denominator 2 underneath both pieces. So it's 1/2 minus cosine 2 theta over 2. It's easier to integrate that way. The 1/2, since we're integrating with respect to theta, is 1/2 theta. And cosine 2 theta over 2 is, the antiderivative is 1/4 sine 2 theta. That one, you can do it with some steps, let u equal 2 theta, but it's so small that you can actually just kind of do a little bit of work in your head. You know that cosine, when you differentiate it, goes to sine, so that's cosine theta goes to sine 2 theta, and you'll know you'll have to divide by 2 again because of the 2 theta. So I divide by 2 again, which gives me another 2 in the denominator, so minus 1/4 sine 2 theta. Alright, so now time to get back the original variable x. That takes a little bit of extra trickiness. We know how to get theta back because theta is equal to the sine inverse of x using our original substitution where x was equal to sine theta. But then sine of 2 theta, we're going to have to use another trig identity. Sine 2 theta is equal to 2 sine theta cosine theta. And then looking at our triangle, Sine theta is the opposite over the hypotenuse, x. And cosine theta is the square root of 1 minus x squared over the hypotenuse, which was 1. So that gives us the full answer. 1/2 sine inverse x minus 1/2 x times the square root of 1 minus x squared plus c. You can double check, take the derivative, and then here's the triangles that we've used so far. When you have the square root of a square minus x squared, then we're going to use this triangle to the right every time. You make the adjacent side the same thing as square root of a squared minus x squared that you saw in the integral. Then the opposite side will be x, and the hypotenuse will be a, the number squared that was squared. Then the u substitution that we'll use will be x equals a sine theta. If you see the triangle, or see the square root a squared plus x squared, you'll have a different setup, and we'll do an example of this one next. You make the hypotenuse the square root of a squared plus x squared, which makes sense because that's what the hypotenuse usually ends up being in the Pythagorean theorem. Then you just pick the sides to be a and x, and the angle theta has the feature that the tangent of that theta is opposite over adjacent, so x over a. Multiplying through by a on both sides, you get x is equal to a tangent theta. And that will be the u substitution that we'll be interested in. So we'll try one of those next.